Now let's just review what our purpose is. So what we are trying to do, up to now we have been discussing magnetostatics. Systems in which the currents were constant, they didn't change, the magnetic fields did not change. So once we create them, they just stay as they are. So what we want to understand now is what should be the laws of magnetodynamics. If we allow the magnetic field to change, what should we modify? Or do we need to modify anything? We had this, for example, the Biot-Savart law. Will it be still valid if the current is changing? Or we had the Coulomb law. Will the Coulomb law be still valid if the charge is moving around, so that it's no longer electrostatics? So how can we describe these new laws that will allow us to describe the electrodynamics or magnetodynamics? So that's our point. And to get some insight on the possible nature of the laws of magnetodynamics or electrodynamics, we consider this system. This is a simple system that we can, in principle, construct. There's nothing that would prevent us from constructing such a system. And the nice thing about this system is, in a particular reference frame, this is a magnetostatic problem. And we believe that we know what are the laws of magnetostatics. So we can study this problem, and we can find what the current is. And the EMF created by this moving rod will be given by this expression. So this is just a magnetostatics problem. But now if we go to another reference frame, this is no longer a magnetostatic problem, because in that reference frame, the magnetic field will be constantly changing. At some point, we have this region of magnetic field. In that new reference frame, this region of magnetic field is moving with a given velocity. So at this point, at a given time, it will have a magnetic field. At the next time, it might not have the magnetic field. So a magnetic field at a given point is time dependent. And in that reference frame, well, the current, the observed current should be the same, or the brightness of the light should be the same, whichever reference frame we choose. So the light just doesn't go off just because we move to a different reference frame. Just because I started to move shouldn't mean that the light goes off. So what I do is I look at this expression. This is the magnetostatic equation, and my problem is a magnetostatic case, so this expression should be valid. What we say is this expression, I can also rewrite exactly the same expression in this form. So this form is exactly equal to that expression in my reference frame. So whether I write the EMF in this form or in this form, nothing changes for me. But in another reference frame, this and this would be completely different. This will be different because in a different reference frame, the velocity of the rod will be different. So EMF will be different, and if the current will be different, etc., which just doesn't make sense. But if you look at this one, if you go to another reference frame, the rate of the change of flux will be exactly the same as this value in my reference frame. So this rate of change of flux as a function of time will be independent of which reference frame I use. So this is a possible law for magnetodynamics, because we know that at least in this simple system, this law gives me consistent predictions, independent of which reference frame I use. So what I would like to conclude at this point is maybe this is a law of nature. This is called the Faraday's law. We will put the minus sign in a moment. Of course, just claiming that this is a law doesn't really mean much. We have to prove that it's actually a law. We have to study its consequences. What will be the consequences of this law if this is a law of nature?
How do we define the area in an arbitrary system?
Let's stick with this one. Let's define do we mean by epsilon, what do we mean by phi b by dt. In this system, and then we can discuss what we mean, how can we define that in an arbitrary system.
Referans frame'e göre değişmediğini söylüyor. Kafam karıştıran bir şey var. Bordun üzerinde dursak, ışığa doğru yaklaşıyor, ışığın yandığını görüyoruz ama üstümüzden ters tarafa doğru giden bir kimse onu daha brighter görmeyecek. Yani
Come here. Look at that light. Okay, run towards it. Does it look brighter? No. Run backwards. Does it look brighter or dimmer? No. Okay, so it doesn't happen. The velocities over here are just like small velocities. You don't need to go to the speed of light. 5 meters per second, let's say.
Zamanın değişeceğini düşündüm de. Hani çünkü eğer daha brighter görürse o zaman ışığın ömrü daha çok kısalacak.
Well, let's say, do you see it brighter? No. Okay. Experimentally disproven.
Well, if the speeds were interesting, we would see.
Hold on. I mean, as I was telling to one of your friends asking me in the break, what we are trying to do is just develop a consistent framework to understand nature. They should be consistent. So I already have a very simple system in which there seems to be some inconsistencies. Let us solve that simple system first. Once we manage to understand how simple systems work, then we can complicate our system and see whether our framework is still consistent in these more complicated cases. Let's stick with the simple cases first. Do we understand how they work? Because once we fix the simple case, most probably we will also fix the more complicated case. Also, historically speaking, when these laws were discovered, there is no relativity yet. There is no speed of light. It's not known. But again, let's first understand the simple problems, and then we will see if we are able to understand the complicated problems or not. Now, first let's look at this EMF. Now, EMF, if you remember our discussion of the batteries, we said that, okay, EMF is positive or negative depending on which way you are moving. So what would you like to call a positive, in this simple system, what would you like to call a positive EMF? A positive EMF, should it run the current clockwise or counterclockwise? Okay, let's say a positive EMF runs the current clockwise. So that is a convention, that is your choice. So we are basically saying that if this rod is moving towards the right, just like this one, it is creating some positive EMF. Now this is the clockwise direction. What should be the positive direction of the flux? Just remember our discussion on the electric flux. If this is a positive current, use your right hand. Whenever you are dealing with magnetic fields, your right hand is one of your best friends. Your right hand, just curl your fingers in the direction of the positive direction of the EMF. So this is the positive flux. So in this case, is the magnetic field positive or negative? In this case, the magnetic flux, is it positive or negative? The magnetic field is in this direction. We said that flux is positive if the magnetic field is in this direction. So the flux is positive. Now, as the rod is moving, is the flux increasing or decreasing?
Decrease.
The flux is decreasing, right? So because the area is decreasing, in magnitude it's decreasing, but the flux is already, we said that it's a positive number, so flux is decreasing. Do you agree? So what we have concluded is that if the flux is decreasing, there is a positive EMF. Do you agree? So that was our conclusion in this discussion. Well, flux is decreasing means d phi b by dt is less than 0. Do you agree? Do you agree that the flux is decreasing means its time derivative is less than 0? So let's see, this is our equality in terms of the magnitudes. Now we can talk about the signs also. You see, if epsilon is positive, d phi b by dt is negative. So putting in the signs, epsilon is equal to minus d phi b by dt. This is the Faraday's law. And here we also said that phi b, this is the general definition. So you have a general area. If there is some magnetic field lines in this area, do you remember how we define this area vector? Perpendicular to the surface. You just divide this area into very small patches, define this ds vector for each one of those patches, calculate the magnetic field at each one of those patches, take their scalar product and sum over all the patches. So this is how we define the magnetic flux. Now, any questions up to this point? Now, let's see the consequences of this law. Let's do an example. No, let's not do an example. Now, any questions on this law before we continue? Now, basically what we can say, as your friend has also pointed out, to explain the simple example, is that in my reference frame, it's the rod that is moving. In the other reference frame, it is the magnetic field lines that are moving. So it's this relative motion that is creating this EMF. And the relative motion is independent of the reference frame. So that's basically what we are actually doing. So as long as you have some relative motion between the magnetic field lines and the charges, let's say, then there is a force acting on your object. Then there will be an EMF created. Now let's consider a case where we don't have any charges, but we only have let's say, a solenoid. We imagine a solenoid What is the direction of the magnetic field created? Upward. Inside this will be the magnetic field lines. Do you remember the magnitude? This will be the magnitude. Now let's just imagine we have a circuit. Let me just look at it from the top. This is my solenoid. This is the direction of the magnetic field. In it, I put some circuit without any batteries. Just some resistance R. And I will allow the current to change as a function of time. Now I have this solenoid. Just imagine this is my circuit with no batteries. And this is my solenoid. I have to feed some current through it to it so that inside there is a magnetic field. I take my circuit and put it in my solenoid. And there's no current running through it. There's no battery in my circuit. That's the critical thing. And let's assume that the area of my circuit is just A. The wires are covering an area A. What is the flux? What's the flux? Well, B0 mu 0 I n times the area. Okay, what is it positive or negative? Well, you can choose whichever one you like. So what would you like your positive area vector to be? If you choose your area vector to be pointing towards you, so this is the area vector is pointing towards you, then this is the positive direction of the current that should be running through my circuit. And phi is positive. Now we can use Faraday's law. This is equal to mu 0 is constant, n is constant, a is constant, minus di by dt. So if the current is increasing in time, so what is di by dt? Positive or negative? Current is increasing in time. Current is increasing, so di by dt is positive. Minus di by dt is negative. EMF is negative. Negative sign just means that it is trying to run a negative current. So the current will be running in this direction. So, okay, so if I is increasing in time, the flux is increasing in time, right? So it was a positive number, and furthermore, it's increasing in time, so its magnitude is getting larger in that direction. Do you agree? Now, let's see. If current is increasing, we had said that there will be the current in my solenoid is increasing. If it is increasing, the current in my circuit will be in this direction, right? In the opposite to this I, because if the I by dt is positive, let me write it down. If di by dt is positive, epsilon is negative, which means I will be negative. That is, the current is running in the opposite direction, to this direction. So although there is no battery in my circuit, due to this changing magnetic field, there should be a current in my circuit, although there is no battery. Well, in this problem, for example, there is no motion, no mechanical motion. Nothing is moving. No mechanical object is moving. But nevertheless, in the previous example, it was due to the motion of some part of the object, part of my system, the rod was moving, that created this EMF. And then we said that, okay, the law of magnetodynamics should be this one. If this is true, the flux might be changing, even if there is no mechanical motion, only if the flux is changing, the magnetic field is changing, the flux will be changing. So it should also create some current, if the previous law is valid. So, and in this case at least, if the magnetic field is increasing because of the increase in the current, there will be a current running in the circuit that I put in my solenoid, and it will create a current in the clockwise sense. Yes?
Since we don't move anything in this, but how is the magnetic box is changing?
We are increasing the current. There is nothing that would prevent me, right? I can increase the current. Okay, so what will be the direction of the magnetic field created by this induced current in my circuit? That is, in this area A, what will be the direction of the magnetic field created by this induced current? I is called the induced current. It is a current created due to the changing magnetic field. And this induced current will create a magnetic field. And within this area A, what will be the direction of the induced magnetic field? Into the screen. So we try to increase the magnetic field in this area, in this direction, by increasing the current. And there was an induced current which just tried to prevent it, because it created an additional magnetic field which kind of tried to resist our increase. Okay, let's just repeat it. We have this solenoid, which inside there is a magnetic field that is going out of the screen. Okay? And inside this solenoid, we put some circuit, which doesn't have any batteries. It's just a loop, this loop with a single resistor. You can just imagine that this is just a lamp. And now we said that, okay, let's just increase the magnetic field over here. How can we do that? Well, the magnetic field in the solenoid depends on the current. So if we increase the current running through our solenoid, then the magnetic field in our solenoid will increase. But the Faraday law tells me that if the magnetic field is changing, the flux that goes through my circuit will be changing. And according to the Faraday's law, this changing magnetic flux should create an induced EMF. And this induced EMF will create a current in my circuit. And using Faraday's law, we said that the EMF is given by mu0 and times the area times minus the rate of change of the current. Now, just as an example, we considered the case if the magnetic field is increasing, this is di by dt is increasing, then we said that the induced EMF will be negative. Well, a negative induced EMF just means that it is trying to run a current not in the positive direction, but in the negative direction. So this I will be running clockwise sense. But if there is a clockwise current in my circuit, it means that it will be creating a magnetic field, an additional magnetic field. You see, we already have one magnetic field created by the current in the solenoid. But now if we change the magnetic field in the solenoid, it is creating an induced current. But we had already seen that by Ampere's law, any current running through a circuit creates a magnetic field. So there will be this additional magnetic field created by this induced current. And this additional current created by this induced current will be pointing into the screen within my circuit, within this area A. So we try to increase the flux going through this area A by increasing the current. So we try to increase it, but that increase in the flux going through the magnetic field A just induced a current that would decrease the flux through the area A. Are you following? No?
The direction should be into the screen or outside?
Which one?
The direction of that induced magnetic.
Well, you see, the induced current is negative, so it is running clockwise sense. So your right hand curl in the direction of the current, curl your fingers. So the induced created magnetic, well, this is a magnetic dipole, by the way. So the created magnetic field is into the screen.
What is the direction of
This one, this is the positive direction of the current. Remember Kirchhoff's rules. There we also assigned some directions to the currents. We said that they were the positive directions of the currents. And so here we also said that since we had chosen the area vector to be pointing in this direction, that fixes the positive direction of the current. The positive direction of the current has to be counterclockwise. But Faraday's law tells me that if the current running through the solenoid is increasing in time, then the induced current should be negative. That negative sign just means that the induced current is not in the positive sense, but it's in the negative sense. So, and the magnetic field created by this induced current is into the screen. So we try to increase the magnetic field in this area but the induced current tried to decrease it. No, they're not exactly equal in general, but it's just trying to resist it. So that is the basis of the Lenz's law. Lenz's law basically states that the induced current tries to resist the change that created it. So the change that created this induced current is an increase in the flux in that direction. So to resist it, the induced current should create an additional field in the opposite direction.
How does it resist it?
Well, you see, we had just said that if you are increasing the flux in that direction, the induced current creates an additional magnetic field in this direction, which creates a negative flux. So the total flux is not as large as it would have been if we didn't have this circuit there.
So another current will peak I will decrease.
Well, let's see, if I will not change. I mean, we are assuming that I is fixed. We are fixing by our outer machinery, outer circuitry. So it fixes I. We are controlling I, this capital I. If we increase that capital I, we are increasing the flux passing through the circuit. So the Lenz law tells me that the induced current in the circuit should be such that it will try to decrease the flux going through the circuit. Well, we will later on see that it also even tries to decrease I. It just tries. Now let's watch a video. Some of you had already watched it in the break yesterday. So you see, so what he has is he has a magnet and he has a copper wire. Hopefully next week I will be bringing this demonstration. We also have it in the Physics Society has it. So let's time how long it takes.
This is a classroom experiment to see how slow the magnet goes down inside the copper.
It still didn't fall. So this is a magnet, a huge one.
1-inch thick N50 disc magnet. And let's see what kind of drag we can create with it. Okay? As you'll see, I have this giant magnet and I have a piece of 1-inch plate of aluminum that I'm going to drop it on. Watch as we drop this and see what happens. One of the really amazing things.
Now that is aluminum. Did you try to stick a magnet to an aluminum? No? Come on, you should try it. Try it and you will see that it's not fun, it doesn't stick. Aluminum is not magnetic. It's not affected by the magnet.
About this, with this 1-inch aluminum slab and the giant magnet, is when you start to pick the magnet up, it feels different. It feels like you're trying to move it through circuit. If we moved fast, this will demonstrate what we talk about the braking effect. You can see
it's not magnetic.
The slightest movement of this generates enough force to slide the entire aluminum plate. But what's really impressive is what it does when we...
Did you see it, by the way?
This magnet.
He didn't touch the aluminum. The aluminum doesn't stick to the magnet. Nevertheless, if you move the magnet or just a few centimeters above the aluminum block, if you move it fast enough, So the aluminum will move with the magnet.
It's 5 pounds, 8 ounces. Yet when I drop it, it's almost silent.
So that magnet is something like 1 kilo or so. And he's dropping it on aluminum. And if you have ever played with these indium magnets, they break very fast, very easily. They are quite brittle. So you wouldn't like to drop a 1 kilogram indium magnet on the floor. So it will just shatter. But if you drop it on this aluminum block, nothing happens. So it just slows down before it falls down, before hitting the aluminum block. It's not the air resistance or drag. It's purely a magnetic effect. So you see that block is already broken. So you see that region. This part over here is broken already. But nevertheless, if you drop it on a conducting block, well, you would like to create large enough current to stop it, so you would rather use a good conductor, and aluminum is a good conductor, although it's not magnetic, so it slows it down.
But now, it actually cushions the fall.
Now let's see how it works.
Very interesting, and you saw it here. Super Magnet Man.
So did you see what's happening? Okay. Now let's try to understand how it works. Now let's do another exercise first. Let's assume we have this magnet. A magnet is nothing but a magnetic dipole. So which should be the north pole? I mean, it doesn't really matter which way you drop the magnet, so you can just choose whichever point as your north pole. Would you like the north pole to be above or below? Above. Okay. So this is the north pole. This is the south pole. So let's draw the magnetic field lines. So these are the magnetic field lines of this magnetic dipole. Now let's just imagine a ring. Not a block, but just a conducting ring over here, below the magnet. So I have this ring. This is my magnet. I'm just dropping it. This is my magnet, this is my ring over here. This is the north pole, this is the south pole. Now, as I lower this magnet, what will happen to the flux? Well, let's say, what is the flux? What's the direction of the flux? What's the sign of the flux? Let's just choose this direction as the positive direction of my current. So this direction is the positive direction of, this is the direction of the area vector. So this is my area vector in this region. Now, at this instant, is the flux positive or negative? Well, the flux is positive because if you look at this magnetic field line, at this point the magnetic field is pointing sort of in the upward direction. So the flux is positive. Now, if I am lowering the magnet, is the flux increasing or decreasing? Why?
There will be more magnetic field lines going up with it.
Yeah. The magnetic field close to the South Pole has a larger magnitude than away from the South Pole, or any one of the poles, in fact. The magnitude gets larger as you approach the poles. So as the magnet is approaching to my ring, the magnetic field is getting larger and larger, so the flux in magnitude is getting larger and larger. We said that the flux is positive. That means if the magnitude is getting larger and larger, the flux is increasing. So EMF, which is minus d phi b by dt, this is less than 0. So which way is the current running? There will be a current in the loop. So this was the positive direction of the current. And based on that, we had said that the area vector is pointing upward. So if the EMF is negative, the current will be negative, so the current should be running in this direction. So this will be the direction of the induced current. Now let's see. Now this is an induced current. We can say that it's a magnetic dipole. What is the south pole of that dipole? So you see, this ring is I can just replace this ring as kind of a magnetic dipole. What is the direction? It's pointing upward or downward, the magnetic dipole? Downward. So this system will be equivalent to the system where I have this magnet, north and south. Here I have the magnetic dipole. And for a magnetic dipole, the north pole is in the direction of the dipole is pointing, the south pole is away from that direction. So the south poles are close to each other. So this current created in my ring will be pushing my magnet away. So it's just like the magnet is a magnetic dipole. This ring, once the current starts running through it, is a magnetic dipole. The magnet has the south pole below, but this induced magnetic dipole has its south above. So the south poles are close to each other. They will repel each other. So that is basically what slows down the magnet in the case of the aluminum. So what happens is you have this aluminum block. This is the aluminum block. You take your magnet, the south pole and the north pole. As the magnet is approaching to your aluminum block, this block you can just imagine as just concentric rings like this. There will be currents running in your block. There will be currents running in the block. And since aluminum is a good conductor for a given EMF, there will be a huge amount of current running through aluminum. And each one of these loops will be pushing your magnet away. If the magnet comes closer, the flux will be larger, the rate of change of flux will be larger. So when it is very close, the induced repulsion due to these induced currents will be enough to prevent the fall of your magnet. So that is why the magnet slows down just before hitting the aluminum block. So these are, by the way, called eddy currents.
It doesn't matter which way it comes back.
Well, in the next hour, let's try the other way around. Let's assume that the north pole approaches first and see what happens. Also, you can also do this, apply the Lenz rule to this. So again, what the Lenz rule says is that the current should be such that it causes the change that created it. So what is the cause that creates these currents? The falling of the magnet. So the currents should be such that they will be slowing down the fall of the magnet. So that's actually what happens. Now let's give a 10-minute break, and after the break we will continue. By the way, is there anybody among you who is a member of the Physics Society?